But first, let's start with a small evolution of the interface, because I think it's interesting to look at how interfaces have developed to know where they're going in the future. In the very beginning, or let's start there, throughout the history of the technical interface, the main objective was to break down the barrier between machine and the human user. It was about easing the communication and to enable the user to achieve whatever task they're set out to do. That's true for every interface, hopefully. In the beginning, the conversation between machine and user was pretty one-sided, with the human speaking more or less the language of the computer, putting in code, putting in print, run, all this kind of stuff. It required the user to understand the grammar of the computer, basically. We then moved on to graphical interfaces, much better to understand, much more intuitive. Symbols, moving two symbols closer to each other would trigger a reaction between both of them. So moving an icon to a garbage bin would delete it, hopefully. At least that was the intention most users had. And that was a big step forward. Within the later years now, we are more moving towards voice interfaces, as I think most of you have maybe dabbled with as well, even if it's just using Siri on your iPhone. And that is basically trying to get as close to human language as possible. We all know how well it's working or not working so far. However, that kind of interface, the voice interface, has made huge progress over the last years. And that is actually extremely impressive, because the way the mind processes language is highly complex. And for a computer to learn that is extremely impressive. But we will get into that later as well. So now, after trying to make interfaces more intuitive and easier to understand and enabling to do the user whatever they want, a lot of companies are actually moving into something in a direction that's called the anticipatory interface. It means not giving the user all the decisions they want. It's not enabling the user to do whatever they want. It's making the decision for them. It's trying to anticipate what the user is going to do, what they're likely to do, what's likely to make them happy, and just remove a lot of the interaction and move them into a systematic level. Slide. Let's talk about the anticipatory interface a little bit more. I guess a lot of you know Nest, one of the best examples of the anticipatory interface. But a lot of these anticipatory approaches are found in a lot of web interfaces lately as well. They can be found in personalization, for example. When you're trying to teach the machine something about you, when the browser remembers you, remembers what you were actually searching for, or where you were on other sites to look for information. What anticipatory design needs is data-driven decision-making. So basically, the system tracks all your environment, the data around you, and tries to create a context based on which it can then anticipate what you're going to do. It's presumptions, assumptions about what you like, and it's based on the assumption that if you do something once, you probably will do it again. And that's what the system wants. It wants you to do the same thing over and over again because that's what it can predict. In order to do that, it needs to be able to actually understand context. In order to be able to understand that you're in a situation you were earlier already, and you did a certain action, it needs to be able to recognize the situation again. That means there's a lot of data collection. There's a lot of watching the environment within which you are moving as a user, and then trying to recreate situations within its own database. Now, what if, instead of looking at the environment and then trying to see from the environment what the user is doing, we could actually look at the user and deduct how the user is seeing the environment and then act upon that? That would be so much nicer, wouldn't it? So that's how brain interfaces are trying to actually approach the whole thing. Disclaimer, I'm not going to talk about actually neurorobotics or neuroprosthetics, which is you think really hard about moving an arm forward and the arm moves forward, because that's working pretty nicely already. And I don't think that's actually the kind of interface that's interesting for us designers. I want to talk more about ubiquitous computing and the systems in which we are moving. Things like smart homes, for example. Basically, all the processes and contexts within which data mining is used and within which anticipatory interfaces are used. But first, let's talk about brain interfaces. So, a brain-machine interface can be described as an artificial process that allows a brain to exchange information directly with an external device. Anyone knows what that means? Or understands, kind of? No? Okay, good. Then let's talk a little bit more about how the brain works then. Basically, the brain is made up out of neurons, and those neurons are attached to each other and communicate to each other through axioms and dendrites, which push ions back and forth to transmit information. That ion back and forth moving is basically creating differences in the electromagnetic current. So that creates electric signals as fast as 250 mph. That's really darn fast. And we have a lot of these neurons in our brain. The assumption is that different parts in our brain are responsible for different actions, activities, or processes. And by watching those neurons and those electromagnetic currents in our brains, to be able to detect what our brain is up to. So basically, every time we think, or we move, or we process something, we have a pattern in our brain, and those can be tracked with the electrons that are basically arranged on the head. This one's actually an interface by Microsoft that's trying to read what kind of word you're thinking. So it's a word processor. It works pretty well. But is it really that straightforward? In order to be able to detect all these patterns in the brain, we have two assumptions. One, that the patterns in the brain are repeatable. So every time we have the same thought, it's going to be the same pattern. And the second, that we are actually able to map them together and map them to a context that makes sense to a machine. So let's talk a little bit more about the stereotypical patterns within the brain. Because the brain is actually a changing thing. The plasticity of the brain depends on the things we know, on the things we learn, on our experiences. Every time we learn something new, the plasticity of our brain changes. And the pattern in our brain changes. And learning is not just a concept or not just a process that appears over time, as a lot of us think about it. It's actually something that happens every day. So there are a lot of micro experiences that we have every day and things we learn in the morning and unlearn overnight. Learning can basically be identified as learning what to discriminate and what to highlight within our brains. Basically, if you wake up in the morning and you're blinded by the light, it's because your visual senses have not learned yet to discriminate the light and to basically approach the light that's coming in the right way. So you're learning that again. Every time you put on a scratchy sweater and you stop noticing it after 5 minutes, your brain has learned to just ignore those signals because they're not relevant to you. That means that this whole thing, this whole organism, is constantly in flux. On the other hand, some things are just really coined into the brain. There are experiences that once we have it, they leave big traces in the brain, and there's no way we can get them out again. Those are memories from childhood, like everything before your 3rd birthday. And they leave stereotypical patterns. But those stereotypical patterns can be very different from person to person, because we all have very different experiences from person to person, right? So that's the two things we have to learn. The personal stereotypical patterns, and also discriminating the learning adoption, basically, that our brain goes through again and again. You're still with me? Cool. Okay, good. So now, moving into the few experiments that I was talking about that I think are extremely interesting for us. Because, as I said, thinking really hard about moving an arm is one thing, but it's not necessarily what we should be interested in as designers, because we want to make it easy for a person to do something. And if basically the user needs to think, okay, I now want to switch on off my light, I now want to bring up the music, it's still a very cognitive task, and they can happen once after the other, because we are not good multitaskers, and it will just keep our brain busy all the time. That's not necessarily a good interface, especially if we're talking about complex systems that try to learn about us. like data mining environments. So instead, it would be really nice if we could read intentions. So before a person actually makes a decision to act on something, it's like, this would be nice, or this is what I want to do. And that's actually possible. So that's possible because there are different parts in our brain that are actually active when we want to do something. What researchers did was asking test persons to decide on one of two tasks: subtracting two numbers or adding two numbers together. They then showed two numbers and predicted what the outcome would be. And they were right. They were able to basically read from the brain if the test person, before seeing the numbers, had decided to go for the subtracting or the editing way. So that basically means that even before the act occurs, even before we know how we want to approach the act, there is an intention that manifests in the brain that we could read, that we could identify. That happens because there are multiple parts to an act in itself. So basically, from a thought to movement, we have three areas of the brain that are involved in that action. We have the prefrontal cortex. The prefrontal cortex is the part that is actually involved in overall high-level conceptual goals. Basically, I want it to be quieter. So the act is, I want to dial down the music. The prefrontal cortex will take care of the high-level stuff, basically. The premotor cortex then will take care of preparing the body to actually conduct the movement. It will activate the experience that we have, the learnings we know about, okay, I need to do that in order to move the arm. And then the motor cortex is the one that actually gets active once we move the arm to dial down the music. So the interesting thing is that that a lot of stuff can happen in the communication between those. Not necessarily must there be a connection between prefrontal cortex and motor cortex. That happens every time we have a reflex. We do something without actually realizing that we were doing it. Because the high conceptual planning, the aware part of it, just disappears. We don't need it. Or it got short-circuited. What also happens is we have an intention. It comes to our cognitive area of the brain, the lateral prefrontal cortex. There's a medial and the prefrontal, lateral. And on the way to the motor cortex, we realize, no, actually, I don't want to do that. I don't want to scratch that itch or whatever. So we can break our action halfway along. Okay, but the summary from this, reading intentions is possible. Awesome. Next experiment. Subjective reality. So I was talking about dialing down the music, and I don't know how many of you had the conversation of you asking someone, could you dial down the music? And they put it down, and you're like, no, that was too much, louder. And they put it up again. No, that was too loud. Pull it down again. That's because we all have very subjective experiences of what's louder, what's colder, what's hotter, or whatever. They are all tied to very subjective perceptual sensations, as well as experiences, and how we actually value the information that comes into our brain. If we would now use brain-computer interfaces and try to identify those stereotypical patterns, we still need to know what the subjective experience of the user is in order to make the right assumptions, what that means. So, basically the part of our brain when we're most actively, unconsciously processing experiences are dreams. So what researchers did was watch people dream, wake them up, and ask them about what they were dreaming. So they basically asked, what did you do during the day? They watched people dream, wake them up, and say, okay, tell me what you just dreamed. And they had basically three versions to compare what was happening. The report before falling asleep, then the processing of the brain during the sleep, because they were able to actually record what was going on in the brain while sleeping, and then the report about that experience, that subjective processing of the dream. That way, it's basically able to establish a mapping, a translation map, between the inputs that are collected during the day and then the emotional processing of it. So, awesome. We don't only have the intentions, we also know what they subjectively mean for the user. So we are very, very close to something that is very, very difficult to achieve with normal interfaces. Third and final experiment. Reading the unconscious. As I said before, if we only focus on what's happening very consciously, it would still be an overburdening experience for the user. It would still be a lot of cognitive load. And we would only be able to actually detect triggers that are so important that they already made it into the conscious processing of the user, into the medial prefrontal cortex. It would be much nicer if we could actually detect, for example, stress triggers before they're so unnerving that the user realizes, I have to do something about it. It would be really cool to actually detect what's going on within the brain that the user just right now does not have the cognitive ability to process. Our ability to actually consciously process information is very limited. There's a whole lot of stuff that goes on unconsciously that we're not aware of. Simply to make our lives easier from our brain side. So that's very nice. But it also means it minimizes our ability to actually act on impulses. There's also one more thing about the brain that's pretty amazing, and that is that it's extremely good at recognizing patterns. And that is something that computers suck at. The human brain can detect context and a lot of different things. Computers still have to figure that out. I earlier said that language is a prime example for that. And it can actually be detected in babies up to like 10 months old, that their brain is so busy just trying to learn language and to learn how to statistically discriminate sounds that sound similar. The thing about context and relationships, for example, between sounds, is that for each of us, our language, our voice is so different, just given from physical things. So my vocal cords are much shorter than probably yours. That means even though we are making the same sound, they are all very different frequencies. But the human brain is actually able to statistically discriminate and say, yeah, but that's probably that sound. Computers cannot, because these groups of vocals are extremely overlapping if you map them just based on physical frequency. So that's what we are much better at than processors. However, we're very slow. Processors are much faster than brains. So in a different experiment, researchers primed testers with one key image and then started to just rapidly flash other visuals at them at a frequency that is too high for the testers to actually differentiate them consciously. They were measuring brain activity while doing that, and the brain was able to detect that pattern unconsciously, even though the tester did not manage to consciously catch the image in all of those rapidly flashing visuals. The brain did, but it never made it to the prefrontal cortex. However, because the processors are so fast, they can actually detect that stimuli and that trigger in the brain and basically say, okay, here, that trigger was registered, even though we weren't aware of that. Imagine a situation where you would have one person observing a big crowd for one face, that person being primed with that face before, and the computer, instead of having camera surveillance on that big crowd of people, just observing the brain and just detecting just from the gaze, as soon as the user gazes at that familiar face, the processor is able to actually detect the trigger. Wouldn't that be nice? Okay, so now we have three different aspects. Reading intentions, reading the subjective experience, and reading unconscious triggers. Those three things are things that are not really achievable just by having ubiquitous systems that measure the environment. So that's an awesome advantage. Of course, there are disadvantages. Of course, there are limitations. All these experiments have just been conducted in a very clean lab environment. So how well they work in the free field is still to be tested, but there's process going on all the time. But it might still take a few decades. But I think for designers, we should be aware of what might be coming. And I think there are also a lot of things in there that are important for anticipatory interfaces. And I want now to discuss the pros and cons of that. So the advantage, of course, are no barrier between the user and the machine. So the user is relieved from the duty to frame their desires and intentions in a way that the computer or the machine can actually understand it. We can finally basically adapt to what the user subjectively mean when they're trying to communicate with the computer. And we can uncover whatever the user is actually not aware of what they need. The issues and the challenges, I think, are actually of a far more high-level ethical approach. If we, let's say, remove the barrier between user and machine, and just reading the intention of a user would mean there's no need for the user to act on an intention. That, in turn, would actively change the plasticity of the brain, because the experience of the act falls flat. And we know that every experience, every act, changes the plasticity of the brain. Would we, in fact, end up changing our brains if we start reading them? Also, if we start to track unconscious triggers, that will mean if they're met before they actually rise to the level of conscious processing, we are basically limiting the choice to make an active choice based on that. We might very much limit our experience in terms of what's around us is nagging us, is stressing us, and therefore also limit our choices and our freedom to change things actively, change them in a different way than they would be anticipated by a machine. And then, of course, we do not only consist of the brain. We consist of a whole lot of other physiological aspects. Hormones, muscles. There's a whole lot more going on, and emotions are actually formed based on a whole lot more than just the brain activity. And we are not measuring that. There are also no experiments right now combining those. So we're leaving out a whole part of the body that if we say we're looking at the human user holistically, it would be a fraud. We are not. Conclusions. I think if we are moving in that way, in that direction, and we are already with the anticipatory interfaces, it cannot only be about convenience. We cannot just make life easier based on that. We just can't take away difficult choices. We can't take away everything that's not nice for us, because then we would actually limit our ability to grow. We need challenges in order to grow. Therefore, we always need to enable the user to actually have a chain out of observation and action. The moment we take away the ability for the user to observe the input they're giving the machine and whatever the machine is making out of it, we're actually removing freedom to analyze what's going on, to understand the bigger concept, to understand the context within which machines are working. If we do that, however, I think it would be actually amazing, and we would have the possibility to open up interfaces for more self-reflection, to learn more about us, to learn more about how we're thinking, what's nagging us, how we're processing things, how we are discriminating things within our brain in a way that this doesn't actually rise to the consciousness. And we could express ourselves in a way that's much more free, because we are relieved from the burden to actually find channels of communication that are meeting whatever the machine needs. All right. That's it. Thank you.